What's up, accelerated chemistry students? This is Mr. Spurk, and this is your chapter 17, section 2 notes, all over measuring and expressing enthalpy changes. So we're going to first talk about calorimetry, and we're actually going to be doing a calorimetry lab tomorrow, right after this lesson. So make sure you pay extra attention and try to get a good feel for it, because this is what our lab is going to focus on. So calorimetry is the measurement of the heat flow into or out of a system for chemical and physical processes. In a calorimetry experiment involving an endothermic process, the heat absorbed by the system is equal to the heat released by its surroundings. The insulated device used to measure the absorption or release of heat in chemical or physical processes is called a calorimeter. So we have these things called constant pressure calorimeters, and foam cups can be used as a simple calorimeter because they don't let out much heat, or they don't allow a lot of heat in, because we know that foam is a good insulator. This is actually what we're going to be doing in the lab tomorrow. The enthalpy, or capital H, of a system accounts for the heat flow of the system at constant pressure. Delta H equals the heat absorbed or the heat released. Heat and enthalpy change mean the same thing, so Q equals delta H. The enthalpy change for the reaction can be written as follows. The heat of the surroundings, which is positive, equals the negative heat of the system. Because remember, the law of thermodynamics, or one of the laws of thermodynamics, says that we cannot create or destroy energy. So if the energy decreases from the surroundings, then it has to increase for the system. So our big equation can be Q of the system equals delta H, which is equal to the negative Q of the surroundings, or that's equal to negative mc delta T. And we know that that is the mass, C is the specific heat, and delta T is the change in temperature. The sign of delta H is positive for an endothermic reaction and negative for an exothermic reaction, much like it is for Q. So we also have constant volume calorimeters. Constant volume using a device called a bomb calorimeter. And a sample is burned at a constant volume in a high pressure environment. Heat released warms the water surrounding the small chamber, thus giving our temperature change. So enthalpy change in a calorimetry experiment. When 25 milliliters of water containing 0.025 moles of HCl at 25 degrees Celsius is added to 25 milliliters of water containing 0.025 moles of NaOH at 25 degrees Celsius in a foam cup calorimeter, a reaction is going to occur. Calculate the enthalpy change in kilojoules during this reaction if the highest temperature observed is 32 degrees Celsius. Assume that the densities of the solutions are 1.00 grams per milliliter, and the volume of the final solution is equal to the sum of the volumes of the reacting solutions. So this is the problem that we're going to work through. And remember that our equation that we're going to use is delta H, or Q, equals negative mc delta T. So we're going to go to a blank slide to do this one. So the first thing we need to do is think about how much water we had. So remember, we have Q equals negative mc delta T. So we need a mass. And our mass of water is what? Let's go back a slide. We have 25 milliliters of water containing HCl and 25 milliliters of water containing NaOH. We know from this piece of information right here that the density is 1.00 grams per milliliter. So that means that 50 milliliters of water, because we have 25 and 25, so 50 milliliters of water is equal to 50 grams of water. So our mass is 50.0 grams. The specific heat of water is 4.184. Sorry, that shouldn't be grams. That is joules. Joule per gram times degrees Celsius times our temperature change, which was 32.0 degrees Celsius minus 25.0 degrees Celsius. So the first thing we need to do is do that temperature change. So we have 50.0 grams times 4.184 joules per gram degree Celsius times with sig figs, this is 7.0 degrees Celsius, because remember when we subtract, we go by the lowest number of decimal places. So now we just need to multiply this through. So Q is equal to negative 1500. And if you type this into your calculator, you're going to get about negative 1464 or 1464. But because of that 7 degrees Celsius, we want 2 sig figs. And if you're unsure of your unit, let's just look through and see what cancels. That gram cancels with the gram, Celsius divided by Celsius. So we're left with just joules, which is exactly what we're looking for. So this system gives off 1500 joules of energy. Because remember, that negative means that this is an exothermic process. So let's look at thermochemical equations. In a chemical equation, the enthalpy change for the reaction can be written as either a reactant or a product. An exothermic reaction of calcium oxide and water is described as the following. We have CaO plus H2O yields calcium hydroxide plus 65.2 kilojoules. A chemical equation that includes the enthalpy change is called a thermochemical equation. Notice that the energy, or the 65 kilojoules, is a product, so that must mean that this is an exothermic reaction, because heat is a product, heat is given off. The heat of reaction is the enthalpy change for the chemical equation exactly as it is written. Heats of reaction are reported as delta H. The physical state of the reactants and products must also be given. Reactions are carried out at standard temperature and pressure. So for heats of reaction, each mole of calcium oxide and water that reacts to form calcium hydroxide produces 65.2 kilojoules of heat. So if we remove it from writing it in the equation, so we just have our normal chemical equation, our heat of reaction, we have CaO solid plus H2O liquid yields calcium hydroxide, which is a solid. And then off to the side, we write our delta H as negative 65.2 kilojoules, because we know that heat is released, so it is negative. In exothermic processes, the chemical potential energy of the reactants is higher than the chemical potential energy of the products. Endothermic processes, such as the decomposition of baking soda, where we have the baking soda plus 85 kilojoules of energy yields Na2CO3 plus H2O plus CO2. This is an endothermic process, and if you remember, we did this in the lab. We had to add heat. Heat was a reactant. So this system absorbed the heat for the reaction to occur. So the 85 kilojoules is a reactant. The amount of heat released or absorbed during a reaction depends on the number of moles of the reactant involved. So if we look at the decomposition of baking soda again, the decomposition of 2 moles of sodium bicarbonate requires 85 kilojoules of heat. So for every 2 moles of sodium bicarbonate to break down or decompose, you need 85 kilojoules of heat. Therefore, the decomposition of 4 moles of the same substance would require twice as much heat, or 170 kilojoules. So let's calculate the amount of heat in kilojoules required to decompose 2.24 moles of sodium bicarbonate. So what do? We always start with what we know. And we know that we have 2.24 moles of sodium bicarbonate. And if we look at our reaction, we can just set up similar. Think back to when we were setting up mole to mole ratios. This is sort of similar. We can say that for every 2 moles of sodium bicarbonate, we have 85 kilojoules of heat. And I just pulled that straight from our balanced chemical equation. So the moles cancels with the moles, and we get an answer of 95 kilojoules. So what this means is that for us to decompose 2.24 moles of sodium bicarbonate, it would require 95 kilojoules of energy. The heat of combustion is the heat of reaction for the complete burning of 1 mole of a substance. Small amounts of natural gas within crude oil are burned off at oil refineries. So you have CH4 gas plus O2 yields CO2 plus H2O plus 890 kilojoules. The heat of combustion, or the delta H, is equal to negative 890 kilojoules. And remember, this is an exothermic process because heat is a product. So what this balanced chemical equation tells us that burning 1 mole of CH4 releases 890 kilojoules. The heat of combustion reaction are also carried out at STP. So in review, the value of delta H of a reaction can be determined by measuring the heat flow of the reaction at a constant pressure. In a chemical equation, the enthalpy change for the reaction can be written as either a reactant or a product. And the Q of the system equals the delta H, which is equal to the negative Q of the surroundings, which equals negative MC delta T. And that's it for section 2. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchemistry.com. Have a great day.